right, good afternoon, everybody. Hello. Let's settle down so we can get started. All right. Hi, my name is Silvina Hanono-Walkman, and I'll be co-lecturing 6004 this semester. So today we're going to actually get into some real meat of the course, which is assembly language and learning about the RISC-V processor specifically and what instructions it supports. And this is going to get you ready to do our first lab, which is going to be released today. So you can all access the lab once we release it later today from our website. You can just go to the labs menu and you'll have links to creating your Git repo as well as to the handout for the lab. Of course, if you haven't signed up for Piazza yet, you should absolutely do that so that you can ask any questions. They tend to be questions that everybody else wants to have answers to as well. And the last thing is that we're going to start to hold lab hours now that the first lab is going out. So if you need help, you can always go to 32083 is our lab room. All right. Any questions before we get started? Yeah. Say that again? It'll be due next Thursday at midnight. So basically, for pretty much all of our labs, you will get it on a Tuesday and it'll be due the following Thursday. And in some weeks, there won't actually be labs. You'll actually have a couple weeks for them. Any other questions? Yeah?
What time is lab hours?
There's a calendar on the website. It shows you exactly when people are going to be working in the lab, and we have a lot of people staffing it, so most of the time there's somebody there. And if there isn't, then let us know if it's a time that you think should be covered, and we can look into that as well. Okay? All right, let's get started. So hopefully, most of you have had some high-level programming, so you're either familiar with Python, maybe with Java, maybe with C, who knows. But what we'd like, ideally, is to be able to build a general-purpose processor that can run programs written in any of these high-level languages, okay? And not only do we want that, but ideally, we want to also be able to not have to make our hardware be overly complex. So we don't want it to support every single feature that is in our high-level languages, only support enough so that we can do everything that we need to do in hardware. So the way that we do this is we basically have what we call a machine language interface. And so this is our interface between our hardware and our software. And essentially what we're going to do is we're going to build a microprocessor that can run everything that's defined in our machine language. And so that's going to be this microprocessor down here. And then we're going to have a software translation step, which is going to take our high-level language and convert it to instructions in our machine language. All right, so let's first start talking about, what makes up a microprocessor. So a microprocessor has essentially three main components. The first is what we call a register file. A register file is basically a piece of storage, but it's not very large and it is very fast, okay? And so we're going to use it in order to store things that we're actively needing to access and not store things that, that we don't need for a while. Those will be stored somewhere else. The second piece is an arithmetic logic unit. So this unit is going to do all the computation for us, the addition, subtraction, comparisons, things like that. And the way that the ALU works is it typically receives two source operands from this register file. It computes a result, and then the output is written back to the register file. In addition to these two components, we have our main memory. So this is where we get the bulk of our storage. So the main memory you can kind of think of as some huge monolithic thing which can basically store everything we want. The problem with that, however, is that it's slow. okay? And so we can store everything we want, but when we need to access it and actually do computations on it, we're going to want to bring our data from main memory into our register file and then do computations on it. And so there's also going to be this interface between our register file and our memory so that we can send data back and forth. The other thing I forgot to mention is that our memory holds two things. It's going to hold both our program and our data. And we'll learn more about that as we proceed. And finally, basically the machine language that we're going to learn about is essentially created to exactly reflect this hardware structure, okay? And so the instructions that you're going to see are going to be specifically dealing with getting registers, feeding them to the arithmetic logic unit, computing some operation, storing it back. Or it'll be something like moving data back and forth between our registers and our memory. So to be a little more precise, what we're going to specify in our microprocessor is first of all the size of our register file. So each register is going to be of a fixed size. Let's for now assume that that's 32 bits wide. We have a small number of registers. Again, let's assume 32. You're going to see this number repeated over and over. And then we have our ALU, which, as I said, can basically take two operators as input. So it can take two different registers, read their values and use those as the source, and then produce an output and write that to yet another register if it wants to. And then our memory can hold pretty much everything we need, so it's on the order of gigabytes or even larger. And finally, we have these two additional types of operations, which we call loads and stores, which are what we use in order to transfer data back and forth between the memory and our registers. All right. So what is an assembly language program? An assembly language program is basically a sequence of very basic instructions, and they're executed sequentially, except for when you have a control flow instruction, which we'll see what that looks like in a minute. So in those cases, you might jump to another piece of the code. But other than that, it's a very simple structure. Each instruction basically consists of one of three things. It's either an ALU instruction, so it's doing some kind of computation. It's a load or store operation, so it's being used to transfer information between memory and our register file. Or it's a controls transfer instruction. And so what do I mean by that? You might want to say something like, if register X1 is less than register X2, then jump to label L in your code, okay? And so we have the ability to do that in our assembly language programs as well. All right, so just to kind of motivate ourselves, let's think about, what would we need to be able to specify in order to take the sum of an array of n elements, okay? So in a high-level program, this would be a very basic thing, right? We have complex data structures like arrays. We have for loops to be able to iterate through things. You can imagine it's fairly easy. So let's see what would be involved in doing this at the machine level. So at the machine level, first of all, you would imagine that your array is not going to be stored in your registers because it might be too large to fit in the register file. So we'll assume that the array or our data is stored in main memory somewhere. And typically it'll be stored in contiguous locations, so one element next to the other. And then we'll use our register file in order to save some intermediate data. So we have to know a few things, right? Like we need to know where is in memory is the first element of my array. How many elements are in my array? And also, I want to keep a running sum somewhere. And so we'll say that we're using these registers X1 through X3 as shown here for those purposes. So what would this program look like? And we're not yet at the level of assembly, but we're getting there, okay? So the first thing we need to do is we need to get some of the information from memory in order to even start off this program. So down here we have some additional pieces of data which tell us where in memory does my array begin, how many elements do I have, and there's also a memory location which is where I want to store my result once I do the sum. And so I start off by basically fetching from memory using these load operations. So I get the value of base, I put that into the x1 register, I put the number of elements into the x2 register, and I initialize x3, which is going to hold my sum, to 0. All right? Now I can start a loop. So in assembly, we have a notion of labels. A label is basically just pointing you to a particular instruction. So this thing here that says loop is basically just the address of the instruction that is doing this load into register x4. Okay? And so in my loop, what am I going to do? I'm going to take the memory element that is pointed to by x1. So what does that mean? So initially, what I put into x1 is the address or the location of the first element of my array. Okay, so what I put into it is this value 4. Right? So in order to access our memory, we have to have a way of specifying which location in memory am I trying to access. And so we do that using this address. And so the value 4 is where I'm loading from, and that's going to put A0 into this x4 register. Okay? I'm now going to take that value that I just loaded, the A0 value, and I'm going to add it to x3 and store that into x3. So far, my x3 value is going to hold just the value of A0. I am then going to add 4 to x1 in order to point to the next location, and we'll talk about in just a minute why that's 4 and not 1. And I'm going to decrement n, which is stored in x2, and then I'm going to say this last instruction basically stands for branch on not equal to 0. So it's basically saying as long as my n has not decremented to 0, repeat this loop. Okay? And finally, when I'm done with the loop, I'm going to take the result that I have in this x3 register, and I'm going to store it back into memory into the location where I wanted to have some. Okay? So looks pretty straightforward. So let's compare a little bit before we get started in the details, some differences between a high-level programming language and assembly language. So as far as our arithmetic operations, the primitive operations, we've got the same exact operations in a high-level language as we do in assembly. Okay? So that's pretty similar. The next thing is in a high-level language we have complex data structures, right? You can define things like arrays, structs, whatever complicated thing you want. In assembly we don't have any such thing, right? We just have memory and locations in memory, and all that we're manipulating are bits or a combination of bits. So you can think of manipulating integers, let's say. Then we have in our high-level language complex control structures, right? We have for loops, we have procedures, we have all kinds of ways of making our programs easier to understand. In assembly, it's really very, very basic. The only kind of control that we have are these basic branch or jump instructions, which we'll see as well. Okay, which just take you to another line in your assembly code. And finally, the high-level languages, they're really very complex, and so they're not suitable to translate directly into hardware, whereas what's good about this machine language is that it is simple enough to actually build a processor that can run all of these instructions, it can do it efficiently, and that way we can have this interface between software and hardware where you're able to translate all of those high-level languages into this machine language that can run on the same processor. But as you can imagine, programming in assembly is not going to be so much fun, and you guys are going to have a taste of this in labs 1 and more in lab 2 than lab 1. And so after doing those 2 labs, I think you'll have a very good understanding for why we don't want to always be programming in assembly language. But it is very important for you guys to understand how it works so that you understand, what it is that we're trying to build and why. All right, so any questions before we continue? All right, great. So we're going to start today now to define what it is that our processor is capable of doing. And we do this by defining what we call an instruction set architecture. An instruction set architecture tells you a few things. It tells you all the kinds of operations that your processor can perform. It tells you about all the storage capabilities that your processor has. And it also tells you how the software is supposed to communicate with the hardware in order to access all these capabilities. And specifically in 6004, we're going to study this RISC-V instruction set architecture, which has become a very popular architecture. It's used for many, many things. The great thing about it is that it's new, it's open, it's free. So it was developed at Berkeley, and there's a lot of support tools for it, and so we can benefit from those as well. Now, the RISC-V architecture has many different variants. We're going to be working with the simplest one, which is known as the 32-bit integer one. But just so you're aware, RISC-V does have 64-bit, 128 version. It's capable of dealing with floating points by having extensions to the basic RISC-V. It's capable of supporting multiply and divide operations, which don't come with a basic package, and so on and so forth. But what we're going to be building is the basic 32-bit integer RISC-V processor, okay? And so by the end of, well, before the end of the semester, you'll actually build the basic processor, and then in your design project, you'll actually have the opportunity to improve its performance by doing things like pipelining, which we'll learn about in this class as well. All right, so now we're going to start talking about, instead of just generally what a processor looks like, what are the specifics of a RISC-V processor, okay? So as we mentioned, we have a register file and a main memory. And I didn't pick the number 32 for no reason. It's actually because everything that we're going to be dealing with in this 32-bit variant of the RISC-V is going to be 32 bits wide, and so we're going to have 32 general purpose registers. Each of them is going to be 32 bits wide. There is one special register, which is this X0 register. It turns out that it's very useful to be able to just access the constant 0. And so X0, if you read from it, it's always equal to 0. If you write to it, it just ignores what you're trying to write. Okay? What about our main memory? So each memory location is also 32 bits wide. And as we mentioned, it's going to store both instructions and data. Okay, so what does this mean? This means that anytime we access a piece of data, we're always accessing 32 bits at a time. It also means that the encoding of our instructions all have to fit into exactly 32 bits. All right, so for historical reasons, though, we complicate things a little bit, and the way that we address our memory is using what's called byte addressing. Now, a byte is 8 bits, whereas what we're trying to access is 32 bits, or 4 bytes, which we also call a word. Okay, and so this is the reason why consecutive locations in our memory are 4 away from each other, because we have 4 bytes for every word. But as far as the way we're going to be manipulating this processor, we're only ever going to be accessing things at this 4-byte boundary. However, in some of these other variants that we're not going to be studying, you can access, a portion of what we call a word, for example. And so the RISC-V itself has the capability of doing that. And so in order to work with that, we want to be able to use byte addressing, which means that every time we access, the next word, it's going to be, as I mentioned, 4 away from the previous one. Was there a question up there, or just stretching? Okay, I think just stretching. All right, so The last thing about our memory is how many locations can we have. So once again, our addresses are 32 bits wide. So this means that we can address 2 to the 32 bytes of memory, which is 2 to the 30th words of memory. Okay, so that gives you a sense for, how big this processor is. All right. Now, we alluded to the fact that we have 3 types of instructions, okay? And so now we're going to take a closer look at them. So the 3 types of instructions that we have are computational, which is basically what it is that our ALU can do. We have loads and stores, which allow us to transfer information back and forth between memory and the register file. And we have control flow, which allows us to jump to another location in our program rather than just executing the next instruction. All right, so let's take a look in detail at what it is that the RISC-V architecture supports. So there's actually 4 different types of ALU operations. So we've got arithmetic operations, comparison operations, logical, and shift operations. And they actually come in 2 different forms. The most basic form is what we call a register-register instruction. So what does this mean? This means that the ALU is going to get its 2 source operands from 2 registers in our register file. Okay? And then the result of the ALU operation is going to go into yet another register or the same one if you want. And so we have 2 source operand registers and 1 destination register. And this is the complete list of computational instructions that are register-to-register instructions that are supported in our RISC-V variant. So as you can see, there's not very many, but with these few instructions, we can actually do every single thing we need to do. Okay? So let's just go over quickly what these stand for. So add and subtract are pretty clear. The comparison ones stand for set less than and set less than unsigned, and we'll talk about what that means. The logical operations, and or exclusive or, who knows what an and operation is? Yeah.
Oh, it compares if 2 things are the same, or if they're both true.
Right.
Yeah.
And so when we say that we're going to do an AND operation, what we mean is we're doing a bitwise AND operation, right? And so if I have 2 registers, each of which is 32 bits wide, then I'm taking the AND, of these 2 bits together, and that will be the result that goes into bit 0 of my result. Then I do the same thing for bit 1. That will produce the next bit, and so on. Okay? And so we're going to constantly be doing logical operations like this on our 32-bit values. And in addition to and or, which you're probably all familiar with, there's also a function called exclusive or. Does anybody know what that stands for? Yeah.
Well, bitwise, it's only true if one of the bits are 1.
Exactly. So one way that I could express that is if I had 2 inputs A and B, and I listed all of their possible values, the exclusive OR function is only 1 when just one of them is 1, and otherwise it's 0. Okay? And we'll see that that function comes in handy for lots of things as well. All right, so the next type of operation is shift operations. And so these acronyms stand for shift left logical, shift right logical, and shift right arithmetic. Again, we'll be going through all of these in recitations, and you're going to become very comfortable with how to use these and what they are. Okay, so the format of them is fairly consistent. It basically, you first specify the operation you want to perform. You then specify your destination register, then your source 1 register, and then your source 2 register. So when you write your assembly instructions, this is what an instruction is actually going to look like. And so here's an example where what this add is trying to do is take the contents of register X1, add them to the contents of register X2, store them in register X3. Okay? All right, how about this, this comparison one? So this one is, what I mentioned stands for set less than. And so basically the way this function works is it's going to compare the two source operands, so x1 and x2. It's going to say, is x1 less than x2? If so, set the result register to 1, otherwise set it to 0. And finally, we also have bitwise logical operations, which you guys are familiar with, and then shift operations, which we'll actually see in motion in the next slide, in fact. Okay, so let's just take a quick example just to make sure that we understand how it is that we're manipulating these zeros and ones, which is basically what all of our data looks like, right? And so last lecture we saw how to represent numbers using 2's complement binary notation. And we also saw how we can go about adding and subtracting these numbers. And so I'll go through this example very quickly. But suppose that instead of, just to keep the example simple, instead of having 32 bits, I'm going to use an example with just 5 bits. And so I have in my x1 register, I have this binary value 00101. Can anyone tell me what that's equal to? 5. How about x2? 3. Good. And so when I perform this add instruction of adding x1 to x2, I'm basically trying to add 5 to 3 and end up with a result 8. And we saw that in binary, you do it very similar to how you would do it in decimal. And I will just run through that very quickly, and you get 8. Any questions about that? Great. Okay. So here's another one, which maybe you haven't seen before. Okay, so this is the shift left logical operation, where it says shift x1 by the number of bits specified in x2 and put the result into x3. Okay, so here's my original x1, right? And it's saying shift this thing to the left by 3 bits, which is the value of x2. Okay, so how does that work? What I'm going to do is, let's first shift by just 1. Okay, so all I did was I took all my bits and I moved them to the left by 1, and I brought in a 0 to the least significant bit. Okay? Pretty easy. If you think about the value of this, can anyone tell me the relationship between the first value and the one on the second row in terms of their relative sizes?
Oh, the second one is
Twice as large, exactly. So this is a very important property that you guys are going to use over and over again, okay? So our basic processor does not support multiplication. However, these shifts and to the left and to the right allow you to do multiplication and division by powers of 2, okay? And so we're going to be using that quite a bit in our assembly language programs. Okay, so far we moved it just by 1 bit. So now we move it 1 more bit. And now let's see what happens when, we shift it the 3rd bit, okay? What happened here is that the one that was in the most significant bit has fallen off the edge, okay? So you want to keep in mind here that we're always dealing with fixed data sizes. So if you're doing a shift to the left, and even if you have a 32-bit wide operand, if you have a 1 in bit 31, and you shift to the left, it's just going to get dropped. Okay, so you want to realize that you're not going to get, this isn't going to turn into a 6-bit value. It's going to continue to be a 5-bit value, or in the case of our actual instructions, 32 bits. Okay? All right, any questions about that? Terrific. Okay, so let's move on to the next type of instruction. So as I mentioned, our computational instructions come in 2 forms. So the first one was register-register, where both of our source operands were coming from registers. And you'll note that those 2 registers could either be the same register or different registers. The hardware supports both. But But it also turns out that it's very often the case that we want to do computational operations with a register and some constant. Okay? And so it's so common that we do this that we actually support a different set of instructions that are called register immediate. And so the format of these instructions is just that the second source register is replaced by a constant. And so they look pretty much just like the other ones are, except that they have this I appended at the end of the operation name, which stands for immediate. Okay, so this is an add immediate of the contents of register x1 to the constant 3 and store that into x3. Okay, so if we look at the list of all the instructions supported in this format, they're almost identical to the register. What's missing? Subtract. Why is subtract missing? Exactly. Okay, so we saw last time that when you use 2's complement arithmetic, subtraction is the same as adding the negative of the number. And so if you wanted to do something like x1 minus 3, you would simply do an add of x1 to the constant negative 3. All right, so let's move on. So now that we have a sense for, what are the operations that we want to do, we need to think about, well, how do we do more complicated things in assembly, right? In a high-level language, I can have a complicated expression like the one I've got here, where I need to first, I increment b by 3, shift it to the right by c, then decrement 1. In assembly, I can't express something so complicated as a single expression. So instead, I have to divide it up into basic operations. So what would it look like for this piece of code? Suppose that, I gave you registers for each one of these variables. And so I'm telling you that A, B, and C are in registers x1, x2, and x3. And then we have these temporary values, which are going to be stored in registers x4 and x5. Okay? So it's pretty easy to see that the first thing I'm going to want to do here is the innermost operation. And so I'm going to add 3 to B and put that into some temporary register. Then I'm going to take that result, shift it by C, put it into another temporary register. And then I'm going to take that and subtract 1 from it and finally put that back in A. So the assembly, for this complex expression actually consists of 3 assembly instructions, which are straightforward to see once we've divided it up into basic operations that only use 2 source operands and 1 destination. Okay. So now let's move on to control flow. So that basically completes all the computational operations we can do. And now the second category is control flow, right? So if I don't want to always be executing instructions one after the other, in our high-level language, I might have an if statement that says, if some condition, do this, otherwise do that. Right? And so the way that we do this in our RISC-V assembly is we have comparison operations, and I'll tell you which comparisons are supported in a second. And the way that the assembly instruction looks is you have the comparison operator, source 1, source 2 are the 2 operands that you're comparing, and then if the comparison returns true, then you jump to label, otherwise you just execute the next instruction. So let's take a look at the operations supported, the comparison operations that are supported by the RISC-V. Okay, so what these acronyms stand for, most of them you can probably guess, but it's basically branch if equal, branch if not equal, branch if less than, branch if greater than or equal to, branch less than unsigned, and branch greater than or equal to unsigned. Okay, so you can tell right away if you look at this chart that it's missing some things, right? Like I don't have a branch on greater than. Why don't I have a branch on greater than? Or how do I deal with it? Yep.
You just use switch the arguments around and use less than.
Exactly, right? So if I had to say branch on greater than, I can just swap my arguments around. I don't need to define another instruction to do that, because it's actually implementing the same thing on my hardware. All right, and so just to see what this code would translate to, what we're saying here is if A is less than B, then I do this then portion. Otherwise, I do the else portion. So who can tell me why the first branch that I have here is a greater than or equal to and not a branch less than? Yep.
Because it jumps to else, not to the then segment.
Exactly, right? If A is less than B, I want to go to the then part of my statement, not to the else. And this instruction is actually jumping to the else label, okay? So basically what this code is doing is it's saying, if A is greater than or equal to B, then go to else. Otherwise, I'm executing this next instruction. And what's this next instruction doing? It's adding the contents of x1, which holds A. It's adding 1 to it, and then it's storing that into register x3, which is where we want to store C. Okay? We'll skip the next instruction for just a second, and then we'll see, what happens in the else. So in the else, again, we very easily can translate B plus 2, C equals B plus 2 to be add I, x3, x2, 2. Right? Everyone good with that? Okay, so now what's this instruction here in the middle? BEQ x0, x0, end. What's that doing? Yep.
If it weren't there, even if we're still in the then branch, we're still execute else, so I want to make sure we don't execute that. So just check that 0 is equal to 0, so it's true, jump to end.
Exactly. Okay, so it's effectively implementing an unconditional branch to end in order to skip the else. Okay, and so we're going to see in a second that actually we do actually support some unconditional jumps, so you don't have to write something like that. And so in addition to our conditional branches that you just saw, we have two types of jump operations which are unconditional. The first one is called JAL, which stands for jump and link. We're going to skip for today what the link refers to. That's going to come in Thursday's lecture. But basically what this is doing is an unconditional jump to this label. Okay? Now, in order to actually encode this instruction in 32 bits, the way that we're storing the information of how far we need to jump is relative to our current location, okay? And so when it says here label is encoded as an offset from current location, that's what it's referring to. And we'll see some examples of that in recitation. And I'll clarify in a second why I'm even highlighting this. So the next type of jump instruction is a jump and link register via register. So what this means is that, again, you're doing an unconditional jump, but this time, instead of just giving a label as your destination, you're giving a register plus a potential constant to add to that register, and that's the address of where you're going to jump to. Okay, so essentially, if you look at this instruction right here, it says jump to the address that's computed by taking the contents of register x1, adding the constant 4 to it, and then that's basically the destination address. Okay? All right, so why is this important? It's important because the second kind of jump supports what we call long jumps. Because of the fact that I'm able to read a register is 32 bits wide, I'm able to specify that I can jump to any location in my entire memory space, because I can put a value that's 32 bits wide into this register, and I can then say jump to the address pointed to by the contents of that register. Okay? Now, what about this jump and link instruction? Could I have, a label that's 2 to the 30 bytes away from my current instruction and somehow encode that for this jump and link instruction? What do we think? Well, hopefully the next slide will help you understand. So, what does it mean to encode our instructions? Okay, so in order to tell our processor what it is that it needs to do, we're basically going to use different bits of our instruction to represent different things. And so our instructions are going to look, they're not going to be exactly in this order, but just to show, I'll put it in this order. So let's say I'm going to have some encoding which is telling me which operation I'm doing. I'm going to have some encoding that's telling me which is my destination register. I'm going to have an encoding of my source register and my other source register, right? All of this has to fit into 32 bits. Okay, so we said that the second kind of computational operation, instead of having a source 2, it had a constant. Okay, clearly by looking at this, you can see that if this entire thing has to be 32 bits wide, this constant cannot be 32 bits. Okay, and so specifically, in RISC-V, because of all of the other variants that we're not making use of, but just you should know that 10 bits are used for the specifying the operation. And then we have some bits for specifying which registers we want to use. So how many bits do I need in order to specify which register I want as my destination? If I have 32 registers, how many bits do I need for that? Yep, exactly. Okay, so 2 to the 5th is 32. So using 5 bits, I'm able to specify which register I'm referring to. Okay, so each of these other fields is going to be 5 bits wide. When this is source 2, then this is also 5 bits. Okay, and in the register immediate case, when this is a constant, this is basically what I have left here, which is what? If I have 10, 5, and 5, what's left for my constant? 12. Okay? So generally, when we're talking about instructions that use these small constants, we're limited to specifying constants that take no more than 12 bits to represent. Okay? So just keep that in mind as you're writing your assembly programs. All right, so in the case, however, of jump and link, back to our jump and link example, so you can imagine that I need some bits to specify that I'm doing a jump and link operation. And I also need to have a register which I'm using for this linking, and so that's another 5 bits. But the way that instruction is encoded is we actually use fewer bits for the operation. We use only 7. Then we have 5 for the destination, so that's a total of 12, and we have 20 bits left over. Okay? So when we do these unconditional jumps via jump and link, the constant that can be specified there is 20 bits wide. Okay? You don't need to memorize all of this. All I'm trying to say is that you have to think a little bit about the size of our constants. And those are the 3 different sizes that we're going to be dealing with. If you have, these small immediate values, they're always 12 bits. When you do a jump and link, you'll have a constant that's 20 bits. And then when you think about, the value of a register, you have the full 32 bits. Okay? And you'll see how that comes into play when you're writing your assembly programs. But any questions about that in the meantime? Yeah?
When we're using a operation represented with constant, assume the constant is interpreted to be signed. So it's filled with ones in the beginning, you begin to define.
Yes. In general, you should assume it is a signed number, but you can use it essentially however you want. So in terms of like the logical operations, it's you can actually use 32 bits that aren't representing a negative value, even if the most significant bit is 1. Okay? All right. All right, so let's continue. So we've gone through our computational instructions and we've gone through control flow instructions. So what's left is talking to memory, okay? So given this explanation right here, you can imagine that my ALU operations can't specify, you know, 2 locations in memory that they want to read and then add and then store them into a 3rd location in memory, because each of those locations in memory requires 32 bits to specify the address, right? So instead of doing that, what we do is we always bring our data from memory into our registers. We then use our computational operations on our registers, which we are able to encode into 32 bits, and then we return the value back to our memory. In addition to dealing with encoding, accessing memory is also very slow. So usually what happens is when you're accessing a particular data element, you're accessing it multiple times. And so it's efficient to bring it from your memory into your register file, access it quickly from your register file multiple times, and then when you're done with it, you store it back to memory. And so in this example, if I'm trying to add B plus C and store that into A, and A, B, and C are locations in memory, the way that I would have to do this is I would have to first load the memory location that is holding B into X1, then I'd have to load the memory location that's holding C into another register X2. I now add these two, store it into X3, and now I can take this result and store it back into memory using my store operation. So a little closer to assembly, but still not exactly assembly, is that when we do loads and stores, what we're specifying is the address of the location in memory that we're trying to access, okay? So when I say load memory B, what I'm actually saying is load the contents that are pointed to by address 0x4, where 0x is the shorthand for hexadecimal, okay? And so this is saying load the contents of address 4 into X1, load the contents of address 8 into X1, and store the contents of X3 into 0x10, which is the address of A. Okay? Questions about that? All right. So that basically leads us to our final 2 instructions, which are loads and stores. And so the format of our load and store operations is a load it's called LW, which stands for load word. There are also load byte and other kinds of operations supported by RISC-V, but not by the 32-bit variant that we're using. So we're always going to only be doing word size loads and stores. So the 2 load and store operations that we'll be using are load word and store word. And the way that they're specified is you give a register, which is used as your base address. You then add some constant to it. That provides the address that you're trying to access. And then the contents of that memory location are put into the register specified by destination. Similarly, for a store, you take the contents of the register pointed to by source, and you put it into the memory location, which is derived from the base register plus offset. Okay? And so what does that mean in our example? If I'm trying to access address 4, the way that I would specify this in the RISC-V processor is I would say take the X0 register, which is always equal to 0, add 4 to it, and load that location into X1. And so this is basically what my load instruction would look like in order to load the value at location 4 from main memory into register X1. Is that clear to everybody? Okay. Terrific. So back to our program for summing array elements. Now that we've seen all the different kinds of operations that we have, we can actually do this in proper assembly now. And so so let's first recall what we had to do. So the first thing we had to do was initialize our X1, X2, and X3 registers, right? So what is X1 going to hold? It's going to hold the address of the next element in the array that we want to access. okay? So initially, we want to put the value 4 into x1. And the way that we do that is by taking the contents of x10, which is holding, this is a little complicated. Let's take a step back. This thing is assuming that the value 100, which is the address of the base, of the location in memory that's holding the base, has already been stored in register x10, okay? So the first thing I have to do is find where in my memory does my array begin, okay? The way that I do that is I first get this base value, and I do that by doing a load of x10 offset by 0, okay? So this says get the contents of address 100, put them into x1, okay? So x1 now has the value of base, which in our particular example happens to be 4, which is where our array begins, okay? Next, we're going to put the value that's at 100 plus 4, which is the number of elements in our array, into the x2 register. Okay, so now we know how many additions we need to do. And then we initialize our x3, which is going to hold our sum, to 0. And now we have our loop, which basically can read the value of the array element it's trying to access by looking at the address that we put into x1 and offsetting it by 0. Okay? And then what we're going to do is every time through the loop, we're going to increment x1 by 4. So the next time through the loop, x1 is already pointing to the next array element. Okay? So I'll let you guys on your own walk through that a little bit to convince yourselves that this is in fact going to add all of those n array elements. And then when you're done, you're going to store them into x3. And so just one last thing that I want to say is that we also have what's called pseudo-instructions, which are aliases to other pre-existing instructions, but they're a little bit more obvious. So for example, a move x2, x1 is equivalent to adding 0 to x1 and putting it into x2. And, and same holds for the rest of these. And